So I'm going to talk about Bohemian matrices in numerical linear algebra, and I'll first begin with a recap on the definition of Bohemian matrices that we've heard earlier. So matrices drawn from a fixed discrete set of small integers, or could be some other discrete set, and we're interested in the sort of intermediate size case. Certainly not n tends goes to infinity, certainly not really tiny n, but sort of medium, small to medium sizes where some computation is necessary. And we're really, from my point of view, looking for insights. So I want to use these matrices to get insights into maybe a numerical method or some property that's of interest, like non-normality. And maybe looking for unexpected behavior or worst cases. The idea being that by focusing on this special class of matrices, we might be able to find things that we wouldn't find if we were just looking sort of everywhere or with random matrices. Perhaps this class of matrices will give us some new insights and some new information. And this, of course, is not a new idea. So I'll mention a couple of, or several ways in which that's the case. So first of all, so many years ago, Olga Taussky was looking at this type of matrix in her research. So here's a couple of papers of hers that I've picked out. The term rational integer there just means integers. And I've quoted some of the things she said. So she was looking in particular at matrices with elements 0 or 1. And you can see her comments here that these are difficult problems that don't yield purely to algebraic methods. So we're going to have to bring in algebra, analysis, geometry, number theory, and matrix theory to understand fully what's going on. So there's quite a variety of different types of maths that could be brought to play here, maybe need to be if we want to get a full understanding of these classes of matrix. One of the places where I first came across Bohemian matrices was actually in this book. I don't know if this is one you've seen before. It's a 1969 book called A Collection of Matrices for Testing Computational Algorithms. And the book consists entirely of printed pages of matrices, obviously small enough to fit on the page, usually, very often, Bohemian, with small integer entries. And typically they would print the eigenvalues. These may have been computed, or they may be exact, or maybe the eigenvectors, or the inverse, or the determinant. So a collection of matrices in which explicit things could be said about the matrix properties. And so that's where I really first came across this this notion of sort of interesting small integer entered matrices. Prior to that, in the previous 10 or 15 years, there'd been a lot of papers published, often very short papers, maybe just one page, where the author would typically describe a matrix or a class of matrices and prove things about it. So here's a paper by Bill Gear, the Gear famous from stiff ordinary differential equations. And he was looking at this class of matrices made up of noughts and ones and possibly minus ones in the top and bottom. And he was able to find properties of that matrix in terms of its eigensystem. So there are many such papers and many such investigations done in the early days of digital computing. MATLAB, actually from the very first version, I guess the first commercial version was 1986, has had Bohemian matrices in it, and a nice class of those is magic squares. So MATLAB has always had this function magic, where you give an integer n and you get back an n by n magic square. The 4x4 version is actually Jorah's famous magic square in that engraving at the top right. And this has the property that every row and every column and the diagonal and anti-diagonal all add up to the same magic number, in this case 34 in the 4x4 case. And this is an article that Cleve wrote in 1993, where he's pointing out various interesting properties of these matrices and talking about how he constructed them. And in fact, there are lots of interesting properties. So if we think in terms of numerical linear algebra, the infinity norm of a matrix is the sum of the absolute values row-wise and the maximum sum. That's clearly equal to the magic sum. The one norm is the column sums. So again, clearly the one norm of the matrix is equal to the magic sum. Turns out the two norm is also equal to the magic sum. In fact, any p norm. So if you look at matrix norms subordinate to the holder p norm, for any p, you get the magic sum. And I was quite amazed when I first came across that property. And the proof is based on the fact that it turns out the log of the norm is a convex function of 1 over p. and that's a consequence of the Riesz-Thorin theorem in functional analysis. So that's not a trivial result, but rather interesting. And so this is a good test case if you're writing algorithms to evaluate or estimate the p-norm of a matrix for p other than 1, 2, and infinity. And I've just shown here one of, I think it was 3 blog posts that Cleve wrote in recent years on magic squares, sort of talking about the various interesting properties and how he generates them in the MATLAB function called magic. So that's a nice example of, I think, Bohemian matrices. And questions about rank also come up here. You know, what are the possible ranks of these magic squares that generated by that particular MATLAB code? So the examples I've given so far are certainly what you would think of as being test matrices. So the Gregory and Karney book is essentially a collection of test matrices. And there's been quite a lot of work over the years on test matrices. I collected, inspired by that book, I collected a number into MATLAB, published in 1991. It's just a set of M files, and I later made that into a toolbox. My aim being to make readily available matrices that could be useful for testing algorithms. Many of these were subsequently incorporated into the MATLAB gallery function. Some other projects, Matrix Market is getting quite old now, but people are still using it. That was a website where you could download interesting matrices. Sweet Sparse is the current name or the new name for what used to be called the University of Florida Sparse Matrix Collection, and that's very widely known and widely used. Large collection of sparse matrices from practical applications, and there's also collections on other types of problem, particularly for example, nonlinear eigenvalue problems. Françoise Tisser and myself have been involved in, and most recently, with my current PhD student Weizhen Zhang, we've made a collection available in Julia form. So test matrices, when Bohemian, are particularly interesting. And so some of the things we're using test matrices for generally in numerical algebra is exploring the behavior of mathematical quantities. It's for testing algorithms and codes to see how they perform, measuring the performance, which might be speed, accuracy, whether they converge if it's an iterative method, and also reproducible research. Now this is a very important topic nowadays, the idea being of course that you can reproduce an experiment that you've done in the past. Bohemian matrices provide an exactly representable set of matrices, so there's no issues over rounding errors in representing them. So it's a class of matrices where you can do an experiment that you can easily repeat later. So in the rest of the talk, really, I'm going to try and use Bohemian matrices to understand or to look at some interesting questions in numerical algebra. And a lot of what I say will be based on this set Sn, which is the matrices with elements -1, 0, or 1. And so the sorts of questions that I would first think of when faced with that set is, you know, how many matrices are singular in the set, or rank 1, or defective, so don't have a complete set of eigenvectors. Symmetric positive definite. This class in general is non-symmetric, but there are lots of symmetric matrices in there. Orthogonal, totally non-negative. Now this is a property that means you take any submatrix and it has determinant that is non-negative. This is a little table I just did last night, a quick computation, because we were talking yesterday at coffee about singular value distributions. So the question sort of came up in my mind of, say for any 4, for the 4x4 matrices from that class, what possible ranks can you get? And here's the answer. And interestingly, most matrices are singular, and in fact most of them have rank 3 rather than 4. So that was just a quick computation done last night. Actually, sorry, this is with 0, 1, because otherwise it would have taken too long. So those sorts of questions are very natural, and I suspect not so much is known about the ranks and such like. But let me focus on something I have thought a bit more about, which is the growth factor for Gaussian elimination. So as you all know, this is a method for, GE is a method for taking a matrix A, converting it to triangular form, and we typically use that in solving linear systems. In practice, we would use some form of pivoting, and one of the major contributions that Jim Wilkinson made many years ago was to help understand the effect of rounding errors on this process. So he was able to show, to derive a backward error bound that involve this quantity rho n. It's called the growth factor, and it's defined as the maximum number that you start with on the bottom, and on the top you've got the maximum number that appears at any stage of the elimination. So there are n stages. A superscript 1 is the original A superscript n is the final upper triangular matrix, and so this is a quantity that's clearly at least 1, and Wilkinson was able to show that that rho n is a very important quantity in determining the stability of elimination. He proved that for partial pivoting, which I'll define in a moment, rho n is at most 2 to the n minus 1, and found a class of matrices that attains the that worst case, which is precisely this, illustrated by this 4x4 matrix here. So clearly a Bohemian matrix. And what happens as you eliminate here is you just get growth of powers of 2 in the last column. But I don't want to talk about partial pivoting, because that's, I won't say well understood, because we still don't understand why it's small in practice, but I want to talk about a different form of pivoting that you may not have heard of, called Rook pivoting. So I'll just illustrate this with this 6x6 matrix, and I'll explain how to get the first pivot. So in partial pivoting, you would just search down the first column for the biggest element, which is 3, and you would then swap rows 1 and 4 to bring the 3 up here. Then you'd add multiples of row 1 to later rows to eliminate below the first, the diagonal in the first column. But Rook pivoting goes a bit further. It asks a bit more of the pivot. So it says, find the biggest element in the first column, and ask, is that the biggest element in the first in that row? Well, it's not, because the 4 is bigger, so we then move to the 4. Then we look down this third column and ask, where is the biggest element in that column? Is it the 4? No, there's a 5 there. Search across this row for the biggest element, which is a 6. Now look in that column, we find a 7. Find the biggest element in the row, which is an 8. Biggest in the column, which is a 9. And now the 9 is the biggest in its column and its row, and so that will be the Rook pivot. So you're finding an element that's the biggest in its row and its column, and you would then swap row 3 and row 1 and column 5 and column 1. So that 9 would move to the 1, 1 position, and then you would do the elimination operations. Now typically the Rook pivoting search doesn't go that far. On average it's between 2 and 3 pivot elements to search before you've found one that satisfies those criteria. So this is an idea that I think goes back to maybe the 1970s or 80s. And Leslie Foster showed in 1997 that the growth factor for this pivoting strategy has that bound, which is much better than 2 to the n minus 1, but he didn't give any cases where that bound is attained or indeed nearly attained. So the question really is, how sharp is that bound? You know, what's the worst case? So this is something we can try and look at with the help of Bohemian matrices. In my 2002 book, I gave in a problem, or the problem of investigating rho n for Rook pivoting, and I gave this little table here, which was based on some simple computations with a direct search method, the nla-group method and similar methods. So by doing a little bit of optimization, I'd obtain these lower bounds on the growth factor. So I had a matrix that achieved growth of 5.36, a 5x5 matrix, for example. So can we do better? By searching over, for example, the set Sn. Well, as we've seen today, the size of these sets grows pretty rapidly. You know, S6 has got 10 to the 17 entries, so we can't get very far with exhaustive search. But let me first of all talk about exhaustive search, because we can do that for at least very, very small values. And so when I first started to think about this, I wanted to do some MATLAB experiments, and I wanted to generate, have a function that would generate matrices from a given population in a way where I could just say, give me the kth matrix from all matrices in this set. And I came up with this function here. Nothing terribly original here, but just one, I think, interesting thing to mention, that the way I've characterized the matrix is via, so here we've got a set with, it's n by n matrices. The vector values determines the population, as Rob called it. So n vals is the number of values, and so d is the length of that set. So d is the number of distinct values that we have to choose from, and so by representing things in base d, you get a fairly concise representation of a matrix in this set. So this way I'm able to say, give me the first, the second, the 100th, or the last entry, the last matrix from this population. Of course, this will only work for reasonably small populations, this idea. But that's how I was able to iterate over the complete set. And so here's how you would use that function. So minus 1, 0, 1 is the population. I've chosen n equals 4. I've just got it to tell me how many matrices there are. Then I've generated the first one, the 1000th one, and the last one. And you can sort of see the pattern. The first one is all minus 1s, the last one is all 1s, and intermediate ones are things in between. So there's nothing very deep there, but that's just a convenient way to do some experiments. Now the problem is, as we know though, we can't get very far in terms of getting n very big if we're going to do an exhaustive search. So there's two alternatives, sampling or optimization. Optimization is really the one I first thought of because I've done this kind of thing in the past when working over the reals. But here, so my variables are integer, minus 1, 0 or 1. So I want to optimize over the set of matrices with these entries, but this is an integer optimization problem or integer programming. And there isn't very much software out there that I can use. One example, one of the few things I found that was applicable was this function GA in the global optimization toolbox for MATLAB. So it uses a genetic algorithm. It's quite a complicated function with lots of options, but if you look at the options carefully, you're able to give upper and lower bounds on the variables, and you can specify variables to be integer valued. So by using these three choices of those parameters, I can get minus 1, 0 and 1 as the set I'm optimizing over. So I was able to do some experiments with that function. And of course, there's a lot of kind of symmetries or the ways you can reduce the set over which you're searching. So for example, in terms of growth factors, there's no point taking upper triangular matrices because they're already in upper triangular form. I can take the 1, 1 entry to be non-negative without loss of generality, and so there are things you can do to reduce the search space a bit. So let me show you what I obtained. So this is the what I had originally 16 years ago. This is by optimizing over the set with that GA function, except for 2 and 3 I was able to do an exhaustive search. So how do these numbers compare? Well, say for n equals 3, the exhaustive search certainly does better than I did with my many years ago optimization. For n is 4 I've not done as well, but for n is 5 I've done better. I've got a growth of 6 rather than 5.36. Random sampling is something I tried as well. So you can sample from the SN or even just random normal 0-1 matrices. And a couple of interesting points here. First of all, random sampling doesn't do as well as optimization. For example, for n is 7 I get 6.5 where I got 10 for optimization. And also, random sampling over SN is doing better than random sampling with rand-n. So this is why Bohemian matrices are interesting for me.
Rand-n is not bounded, right? The numbers in
These are just normal 0-1. Yeah.
But they're not bounded.
No. But this is what you would first think of if someone said, do some random sampling and check the growth factor. That's what most people would do, or maybe rand. But we're actually doing better by randomizing or random sampling from SN here. So that's a way we can get some insight into growth factors. I think we still don't understand the growth factor for Rook pivoting and how big it can be, but these experiments and more of this type could certainly do give some insight. This is a paper from, an article in Science News from 1987 by Eric Gross and Cleve, and they were reporting a matrix on which ISPAC, which was currently then the standard state-of-the-art eigenvalue solver, ISPAC failed. So a 9x9 matrix with elements 0 and 1, symmetric Hankel, and on one particular computer it failed due to what turned out to be an underflow. And this had arisen in experiments by Ziegler and Oddzico, looking at ranks of these matrices. So that's a good example of where using these sorts of matrices can expose problems with algorithms. So there's a detailed explanation in that article there. Paper by Graham and Sloan. They talk about anti-Hadamard matrices. So a Hadamard matrix is a matrix with elements -1 and 1 whose columns are mutually orthogonal. So an anti-Hadamard matrix, as they define the idea, is a 0-1 matrix for which the norm of A inverse is maximal. That's just a rough definition because they also try to maximise determinants as well in that paper. So this is a very nice paper with lots of not only experiments but also theorems and proofs. So I wrote a function called Dramadar because it's Hadamard backwards and I wanted a short term. And this has made its way into the MATLAB gallery function. So there's the help for it there, or the first part of it. So there's 3 values of k you can take to get 3 different types of anti-Hadamard matrix. And just let me show you some examples. So the type 1 matrix is Toeplitz. And this is meant to have a large inverse. So here's the matrix, here's the inverse. And you can see there's a 5 in the top right-hand corner. So that's, I think, about the best you can do in terms of getting large entries for that size of matrix of that type. The type 2 is upper triangular. And again, 5 turns out to be the maximum element. Of course, these small examples don't necessarily give you a feel for the actual growth of the entries of the inverse, but the paper gives lots of estimates as n gets bigger. And the third class is Toeplitz low Hessenberg. And in this case, it's the determinant that has been made big. So you get a determinant of 8. And interestingly, you get some rather nice curves if you plot the eigenvalues. So these anti-Hadamard matrices are quite well studied. And here's a paper that gives one of these n goes to infinity type results, which is not really what we're concerned with here, but I just wanted to give you a feel for that. So Allen and Vu, 1997. So the largest element of the inverse of a matrix with elements 0 and 1 looks like n to the power n over 2 plus little o n. So that's giving you an idea of the growth of the largest element as n goes to infinity, and hence various norms can be bounded that way as well. So there is a lot of literature of that type, of which I think I'm probably only partly aware. So in numerical algebra, normality is something we always worry about. A matrix is normal if, the standard definition, if A times the conjugate transpose A star equals A star times A. But we often think of that as a matrix is normal if it has a complete set of if there exists a complete set of orthogonal eigenvectors or unitary eigenvectors. Or equivalently, A is unitarily diagonalizable. And the problem is that matrices that are not normal can be rather nasty for many algorithms. For example, iterative algorithms, eigenvalue computations. We know that symmetric or skew-symmetric or orthogonal matrices are normal. Beyond that, there's not a lot that we think of. So I don't have a good feel for what the complete set of normal matrices looks like once you get beyond those sorts of classes. So one computation I've done here is for Sn and for also Pn, the 0-1 matrices, just to count how many normal matrices there are in these classes. So for NH 4, we've got 75,000 4x4 normal matrices in Sn, and here's a typical one about which there's really nothing special. It's not symmetric, it's not orthogonal, it's not skew-symmetric, it's just a general normal matrix, and there are a lot of them. And for Pn, of course the numbers are much smaller here, but there's over 1,000 4x4 normal 0-1 matrices. So that's something that we don't normally see somehow, those sorts of normal matrices. What about non-normality? And indeed, how do we even quantify non-normality? Well, Henrici in 1962 proposed a definition of departure from normality. So the idea is you take the Frobenius norm squared minus the sum of the squares of the eigenvalues. The best way to think of that is in terms of the Schur decomposition. So you transform A via the unitary Q to triangular form, and the non-normality is the norm of the strictly upper triangular factor, or the strictly upper triangular part of T there. So if you had a normal matrix, T would be diagonal, n would be 0, and so delta of A would be 0. So how big can delta A be, in particular for a particular class of Bohemian matrices? Well, if we take Sn, the -1, 0, 1 matrices, then clearly this is bounded by n. Why? Well, this is n squared, and we're taking something off. So clearly it's bounded above by n. So how close to n can it get? Well, when I first thought about this, my guess was that matrix there might be a worst case.
Just take a Jordan block with those.
So this is upper triangular, I've made the upper triangle as big as I can, the upper triangular part n as big as I can, and I don't really care what's on the diagonal. You can take any matrices from, any elements from the set there. So that's a first guess. Maybe that would be a bad case. And here's the value of the Henrici departure from normality of that matrix. I've called that G sub n. Now let's compare what we get by doing a genetic optimization with the MATLAB GA function over Sn. So maximizing, letting MATLAB maximize the individual elements. So each element of S has got 3 possible values, and it will try and choose them to maximize this quantity. So for N is 4, it came up with that matrix, which has a value of H of A is 4. So this beats my guess easily. So there's the matrix. If you look at the Jordan form, all the eigenvalues are 0, and there's a 3 by 3 block corresponding to eigenvalue 0. Try N is 5. Again, we get something bigger than what my guess gave me. Interestingly, no zeros in this matrix. But again, well, what are the eigenvalues? We've got a single 1 and then 4 zeros. And for N is 6, we get all 0 eigenvalues and quite a big Jordan block again. So the observation I can make from this, and I think went to 7 and 8 as well, is that for even n, we seem to get all 0 eigenvalues and the departure equals n, whereas for odd n, we seem to get a single 1 as an eigenvalue and root n squared minus 1 as the departure from normality. However, what are these things? They're just the output of this function GA. I don't know what they are. They might be a local minimum, global minimum, who knows? The function doesn't tell you. So I'm not claiming that these are in any sense optimal, but it's just interesting that there is a pattern starting to emerge here, which I haven't investigated any further, but there may be something to be proved perhaps from that. Ill conditioning we also worry about in numerical algebra a lot, and in fact this matrix Tn we're well aware is a rather nasty matrix. It looks pretty innocuous, but when you invert it, the numbers get bigger towards the top right hand corner, and you get a 2 to the n minus 2 there. So as soon as n gets any reasonable size, this is a pretty ill-conditioned matrix. So is that a worst case? Well, let's try optimization again and see how big we can get the condition number for matrices in Sn. So here's what was returned by the function GA. Now I've inverted it symbolically just to make sure I get the exact answer and get integers using the MATLAB symbolic toolbox. So there's the inverse of that matrix. So the condition number of this matrix here is 40 versus 32 for that triangular matrix I just showed you. So it's certainly doing better than the triangular case. 5 by 5. So we've got, I think, a maximum element 9 here. So 150 condition number versus 80 for the triangular case. And then the last one, N is 6. There's the matrix that comes out from Sn, and we're starting to get some decent sized numbers here. So again, we're getting a more ill-conditioned matrix. These matrices all have determinant plus or minus 1. So is that necessary for a maximum to be obtained? It's a reasonable guess, because if you think about the definition of inverse in terms of determinants, which I don't like to think of determinants, but there's a det A on the bottom, there's a minor on the top. Making det A 1 on the bottom is somehow making the elements big, but that's just a very crude way of thinking. So is there anything more you can say about that possible, or about that observation? Certainly that's what we're getting from this optimization. So those are the values I came up with, and I guess the point is, for any 16, we're getting a much more ill-conditioned matrix than the triangular one that I thought was already a pretty bad example. So there are some pretty ill-conditioned matrices in this set, as well as lots of singular matrices as well, of course. Correlation matrices, a completely different topic. This is something I've worked on quite a bit over the last 10 or 15 years. So what is a correlation matrix? It's a symmetric matrix with ones on the diagonal that is also positive semi-definite. So that's a simple definition. So there's a matrix, and I'll ask you, is that a correlation matrix? It's symmetric, it's got ones on the diagonal, so the only question is about the signs of the eigenvalues. So are all the eigenvalues non-negative or not?
It's a tridiagonal triplet, so you know the eigenvalues.
Mm-hmm.
Well,
It's not obvious to me when I first think about this. I just can't say, oh, the eigenvalues in my head or whatever, but it turns out there's quite a large negative eigenvalue there. So that is not a correlation matrix. And in fact, if you put a parameter in here and vary it, you find you have to have a 1 there. So if you just change this 0, the only value that will work to make it a correlation matrix is a 1. So correlation matrices are interesting, first of all, in the sense that it's not easy to tell if a matrix is a correlation matrix. Secondly, there's many applications nowadays, in finance certainly, but also in many other subjects where in data science you often want to ask, are things correlated? So it's just a question that comes up very often. So all kinds of questions to do with correlation matrices are interesting. And here I'm just going to ask, how many are there? How many correlation matrices are there in a particular Bohemian matrix family? So here, if we take the family as Aij is 0 or 1, this is by enumeration. So this is the number of correlation matrices, this is the total number of matrices, and the proportion. So the proportion is going down. So here's a 6 by 6 correlation matrix that was found via this search. And there's nothing special about this, other than the fact that it's not obvious that's a correlation matrix. In fact, it's singular. It's got eigenvalues 5, 1, and 4 zeros, and a somewhat arbitrary pattern of 1s and 0s in there. So often we are interested with correlation matrices in extreme cases. So of course this means extreme correlations plus 1. So if this was a correlation matrix of, in the world of finance, it would mean certain shares or whatever are fully correlated. So these extreme cases are certainly things that people are interested in. And the final topic is again different and somewhat subtle. So the general point here is, or question, if we compute some function of a matrix and we know that there should be some structure there, but we don't actually quite get the structure because of rounding errors, or indeed some other errors, is it safe to perturb it back to have the structure? And perturbing back would typically be projecting back onto. So I'll give an example in a moment. I wrote a Science news column end of last year on this very topic. So what's an example? Well, determinants. So if you have a Bohemian matrix, integer entries, then the determinant is an integer. But if you compute data in MATLAB, what it's going to do is do an LU factorization with partial pivoting. PA is LU, P a permutation matrix. And this implies that det of A is plus or minus det of U, because L is lower triangular with 1s on the diagonal. So det of A can be obtained from det of U. So here's an example. The Pascal matrix is a very nice matrix that's built into MATLAB. In the anti-diagonals, you've got the coefficients of Pascal's triangle. And it's not hard to show that this matrix has determinant 1 for any n. So here's the 14 by 14 version. A is Pascal n. Det of A comes back as 0.99998. Well, obviously that's 1 within rounding error. N is 16, det of A 1.0046. So again, we know what the answer should be. You just take the nearest integer, little bit of rounding error is no problem. N is 19, minus 2.99. So the idea of just mentally rounding to the nearest integer suddenly completely fails, and you would be misleading yourself if you thought that that was really minus 3. So you have to be a bit careful when doing computations in floating point with integer matrices or problems where the answer is an integer. You certainly can't just round to the nearest integer. This is a gist on GitHub, just a sort of standalone file that I put up there. And it's a matrix that Alan Edelman came up with. So it's a 27 by 27 matrix of 1s and minus 1s, a classic Bohemian matrix. So why is it interesting? Well, Alan observed the following. So here I'm loading the matrix into MATLAB, computing the determinant, and there it is. So it's an integer, as expected. So I would have just said, fine, MATLAB has clearly given the right answer. But Alan didn't take that as given. He thought for a moment and he said, how's the determinant defined? the determinant can be defined as a sum of n factorial terms, where each term is that product of aij's, where you take a single a from each column, in a different column. So the standard definition of determinant as a sum of products of aij's. Think of it that way, and we've got 27 factorial terms in the sum, and each term is a product of 1s and minus 1s. So that's an even sum of odd integers, which must be even. So by that argument, the determinant is even, whereas we've got an odd determinant. So this is the wrong answer. So you might have thought that was correct, but it's actually wrong. It should be a 0, not a 1 as the last digit. So should we be complaining to MathWorks about MATLAB, failing in this example? Well, not really. If you look carefully at the analysis of all this, look at the rounding error analysis. This is, of course, a tiny relative error in such a 15-digit number. So this is entirely within the bounds that round-off error analysis suggests. It's just that the fact that it printed as an integer could mislead us into thinking we've got an exact answer when we haven't. If you want to know more, I've got a blog post which you can get to by clicking that icon, all about this example with some analysis. So that's a rather salutary example of the care that's needed when working with integer problems in floating point. So there's nothing wrong with the det function, it's just the rather subtle effects of rounding errors. So we need to be careful. So my last example is one that came up really in the context of a number of recent pieces of work where we've been doing experiments with matrices where we vary the condition number. So we want to have dense matrices where we can specify the two-norm condition number. And the standard way of doing this is with, well, in MATLAB it's gallery randus VD. Basically you choose your singular values, you put them on diagonal of a matrix, then you pre and post multiply by random orthogonal matrices chosen from the Haar distribution. And that's what that function does. There's a function in LEPAT that does this, so it's a standard technique. Goes back to at least Pete Stewart in the 1970s. And you can choose your singular value distribution. But in the work we were doing, we were actually using the infinity norm to measure errors. So although we were generating matrices with given two-norm condition number, it was really the infinity norm condition number that we wanted to tabulate. So how much can they differ? Well, we have this well-known inequality for norms. So the two-norm and infinity norm of a n by n matrix can't differ by more than root n. And from that it follows that the condition numbers can't differ by more than a factor n. But we've observed that typically, for matrices generated this way, the two-norm is less than or equal to kappa. So kappa is always at least as big as the two-norm condition number, even though this inequality suggests it could be a factor n smaller. So it raises the question, how sharp are these inequalities? So let's have a look, see what we can say. Well, a special case is Hadamard matrices, elements plus or minus 1, mutually orthogonal rows or columns. For these, it's easy to see that the two-norm condition number is 1, the infinity norm is n. So that's an extreme case where the infinity norm is as big as it can be relative to the two-norm. But of course, Hadamard matrices don't exist for all n. There's an open question about for what n they exist. For a normal matrix, we understand what's going on because we know that the two-norm is the spectral radius, and the spectral radius is bounded above by any norm, in particular the infinity norm. So for a normal matrix, again, kappa 2a is less than or equal to kappa infinity. So what about the other direction? Can we make kappa infinity smaller than kappa a? Well, I've thought about this a bit, and when you think about it, you think, well, the infinity norm is based on row sums, so a bad case, or a good case, if I'm trying to make the infinity norm small, would be to have the columns lining up, but not the rows. So here, the one norm would be big, but the infinity norm would be small. And I want to make the matrix non-singular, so I put epsilons here and here. And for this matrix, you get n over 2, roughly, as the difference. But remember, n was what was in the bound. So the questions that remain, can we actually get a factor n difference here? And why do we often find in practice that, despite this example, the matrices we generate typically have bigger infinity norm than two-norm condition number? I don't know. So that's still a bit of a mystery, and an open question that maybe people will have ideas about. So to finish off, just let me give a perspective and mention some problems. So I would say the Bohemian matrices already play a central role in numerical algebra, even if they've not been named so. But you'll find the Wilkinson matrix, for example, that gives the worst case for partial pivoting in many papers and textbooks. And so my feeling is it's always worth trying matrices from these sorts of classes, rather than just the typical rand or rand n, if you want to understand what's going on with your algorithm, your theorem, or whatever it might be. And random sampling, exhaustive search, optimization over integer values, all are quite promising approaches. And the optimization I think is particularly interesting, but I still don't know a really good way to do it. I'm not that keen on genetic algorithms because I don't really understand what's known about what they provide. You know, there's not so much in convergence theory for those algorithms. So I'm getting something back, but I don't know whether it's a local maximum, global maximum, or what. So open problems then. So what's the best way to optimize over a Bohemian set? As I've just mentioned, I think there may be better ways of doing that. Are there more matrices we should put in MATLAB's gallery, or suggested the MathWorks that they put in there? There's about 63 matrices right now. There seem to be lots of other interesting matrices around. So, you know, are they sufficiently interesting that they would add something different to what's available in MATLAB? And then there's the particular questions I mentioned as I've gone through the talk, finishing up on that kappa 2 versus kappa infinity a question. And I've got some references at the end of the talk if anybody wants to see any more. Okay, so I will stop there. Thank you.